everyone. So this is another live Q&A for MATH1055. Let me just fix my webcam. Yeah, it's much better. Okay, so you have all seen that the third homework sheet is now available. The submission deadline is the 5th of November at 2 p.m. In the meantime, we also have this week 5 module check-in, which is your chance to give me feedback, and many of you already did, and I'm very grateful for your comments, the nice ones and the not so nice ones as well. Have been very useful because at least they are constructive criticism, which is always a good thing to receive. I think the major point many of you made is this lack of practice problems. Well, the quantity of them not being enough, or you think there is not enough of worked examples, or that the difficulty level of your homework problems is not necessarily the same as the practice problems. So these are, of course, personal. I mean, can be different from person to person. This is very relative. What is considered to be hard and easy? It's clear that many of you think this way, so there must be something to it. I will try to share more and more worked examples, or at least give you more resources. Of course, there is only so much one person can do, so, and I'm mostly alone in this one. I have of course some helpers, as in the tutors, the tutorial groups. And one thing that I should make clear is that lectures are for the theory stuff. So please don't expect the lectures to turn into tutorials and sessions where we'll solve worked examples for 50 minutes. This is not what lectures are for. I'm sure you've seen other lectures as well. So the lectures should help you, get better at the theoretical side of things. But of course, solving problems is also important. And if you ever feel that you are struggling with a problem, that is a good sign. So please do not think that just because you can't solve a problem right away, you are failing in some way. If you could solve all the problems right away, that would mean that you are not learning anything new, or that the problems are way too easy, and this module is the thing that is failing. Okay, so struggling is a very important component of learning. Any sort of learning comes with struggle, and in maths we especially struggle a lot when we encounter new concepts or new techniques. So please do not think that struggling is something that's tells you that you are not good enough. If you struggle, that's good. But yes, at some point there should come some understanding of these things, and I hope that all of this struggle will be worth worth the time. Okay. If you have any questions, just let me know in the chat. Let's move on to these questions that we usually do. In the meantime, if I see questions being asked, I will try to answer them. So please go to the usual place, which is itempool.com. What is it? There is it. There it is. itempool.com/math1055/live, and try to answer this question or compute this limit, which is, well, it looks fairly complicated. It's the limit of the sequence, that is the ratio of two polynomials. In the numerator, you have 2n n to the fourth minus 3n cubed plus n minus 1, and in the denominator, so this is divided by 7 times n to the fourth plus 5n squared plus 2n minus 4. Okay, so you can see that both the numerator and the denominator go to infinity as n increases. So these numbers, both upstairs and downstairs, get larger and larger. What we are interested in is the ratio, which number does it tend to? And of course, by now you know that it does not necessarily have to tend to any number. It could diverge, which means that there is no number which it converges, or it could diverge to plus infinity or minus infinity. And in those cases, if you think this is going to plus infinity, you should write inf, the word inf, in that box. If you think it goes to minus infinity, just write minus inf in the box. Okay, so I already see a fair number of people submitting their answers. That's good. So with these sort of limits, what you have to consider, what you have to think about is, first you have to identify the terms, the expressions, which are dominating as n gets larger and larger. Okay, so n goes to infinity, and as n gets larger and larger, there will be certain terms in this expression which will dominate every other term, so which will really be responsible for the value of this fraction. Okay, so try to think of it that way, and I will show you how to deal with such limits after we have finished this poll. In the meantime, again, if you have questions, just feel free to ask them. I will try to look at the chat as well. Okay, so I guess there is something like 60 people who have already voted for something, and which means that there is still 40 something of you who haven't done so. By all means, please go to this website, itempool.com/math1055/live, and you can participate in these interactive questions. So again, we are calculating the limit of a fraction of a sequence which has entries given by this general expression, and the entries are fractions. And what we basically have is two degree 4 polynomials of n divided by one another. All right, so I think there's a large enough number of submissions, so I could maybe just finish the poll. Let me finish it because we have many go through. Okay, so I see that the majority of the answers, 49 of you, got it right. So let me try to give you a quick look at this problem. So a limit that we had to consider was 2 to the n, 2 times n to the 4 minus 3 n cubed plus n minus 1 divided by 7 times n to the power 4 plus 5 times n squared plus 2n minus 4. Okay, as n goes to infinity, we are interested in this value. So what I suggested that you do is identify the dominating expressions, and of course it's n to the 4 that grows the quickest when n goes to infinity. When n gets larger and larger, it's the 4th power of n which will dominate both the numerator and the denominator. So pulling out n to the 4 from both the numerator and the denominator will leave you with 2 minus 3 divided by n plus 1 divided by n cubed minus 1 divided by n to the power 4 divided by 7 plus 5 divided by n squared plus 2 divided by n cubed, what is it, minus 4 divided by n to the power 4. So the reason I did this, pulled out the dominating terms, the dominating powers of n, is that this way we can simplify by n to the power 4, and what we have is the ratio of two things which behave nicely when you take n to infinity. You can see that all of these terms go to 0 as n goes to infinity. So the only thing that doesn't go to 0 is 2 and 7. So in the limit, these will all go to 0. And what we are left with is 2 over 7. Okay, so this is just 2 over 7 for that reason. And you can deal with such limits in the same way, just by identifying the dominating terms. Okay, I hope that was clear. Let's try to move on to the next question. And this is a true or false question. There is a statement. It says that if the limit of the sequence an is L, then the limit of the sequence that we get by shifting the index by 1, so an plus 1, is also L. Okay, so you should decide that if this statement is true or false. In these problems, what you have to do, if you think it's true, that means you should be able to prove this statement. You should be able to come up with a mathematical proof for this. If you think it's false, then you can falsify it by basically just coming up with a counterexample, coming up with an example which shows that this statement is not true in general. So you would have a sequence an which has a limit L, and if you would consider the sequence that is obtained by shifting the index by 1, which means that we just ignore the first term from the original sequence, that wouldn't go to L. Okay, so that is what it means to come up with a counterexample. So if you think it's true, this statement, you should be able to prove it. If you think it's false, you should be able to come up with a counterexample. Okay, so this is how these true or false questions or problems will work. In the meantime, I'll just make some notes. So if the limit of the sequence an as n goes to infinity is L, then the limit of an plus 1 should be also L. That is the statement. And we'll see which one is correct, whether it's true or false. So this question is a perfect example, the first question in which we really have to use the definition of convergence. And I guess that's the trickiest definition in this module, because it involves lots of moving parts. You know, for all epsilon, you have to have this special index capital N, and so on and so forth. So it's sort of at first glance, it might seem like a complicated statement, a complicated definition, but it's really not that difficult. It's just trying to make this idea of a sequence getting closer and closer to a number precise. So that's all it does, really. Okay, so again, I see there's something like almost 80 of you. Yes, there is this recurring theme of calculators fooling you or tricking you into giving the wrong answer. Please do not trust your calculators. Trust your minds. Trust your intuition more than your calculator. And just simply try to get a good idea, a feeling for these definitions. I mean, these are not, you know, incomprehensible things. People came up with these definitions to make sense of things. So please try to make sense of these definitions. Okay, let's see. There's 80 submissions at the moment. Let me finish the poll and reveal the answer. So this is true. So why is it true, this statement? Oops, let's see. So here is the statement. It says that if you have a convergent sequence that converges to a limit L, then basically just forgetting, so there's the sequence A1, A2, A3, A4, and so on. These are the first 5 terms of the original sequence, and these numbers go to get closer and closer to this number L, and they can get arbitrarily close to that number L. That's the point of convergence. And this second sequence, imagine n going through the natural numbers 1, 2, 3, and so on. You just get these numbers. Basically, just omitting the first one gives you this sequence. Okay, so let's see first the definition of convergence. So what this thing here is just that, and I'm going to use symbols, but don't be afraid. I'm going to say them in words as well. So for all epsilon that are positive, there exists a special index, capital N, such that the nth term of the sequence is closer to L than epsilon for all indices, little n, that come after capital N. Okay, so you see I'm writing all these symbols, but I'm actually saying words. I'm actually, you know, saying it in proper, I guess, proper English. So what does this mean? Well, it means that if someone gives us an epsilon, a positive number, so just imagine someone giving you a really small positive number, you should be able to find an index after which all terms in the sequence are closer to L than that previously fixed small number. Okay? So imagine that we have an epsilon. So we fix an epsilon. Let me move it so you can all see it. Fix an epsilon. Then, of course, there is this n for which the original sequence is closer to L than epsilon. So what what special index should we choose for our new sequence an+1? Well, if you think about it, think a bit. It should be basically n capital N minus 1. Because if what did I say? No, sorry, capital N plus 1. So because if little n is greater than capital N, then n plus 1 is greater than capital N plus 1. Okay, so which means that for a n plus 1 will be closer to L than epsilon for all little n plus 1 greater than capital N plus 1. Okay, so all that this is just reformulating the original definition of convergence by shifting this index by 1. Okay, I hope this was clear. We'll see questions like this later on, so don't be afraid if you didn't get that. Yes, I'll tell you about that. So in the meantime, we have another limit to compute. So go to itempool.com/math1055/live to look at the next question. So in the meantime, I'll tell you about this epsilon. So the whole point of convergence, again, is that you have a sequence of real numbers, a sequence of numbers that get closer and closer to some other number, the limit of that sequence, if the sequence is convergent. And the point is that the numbers in that sequence can get arbitrarily close to the limit. How would you quantify that? Getting arbitrarily close as you want? Well, you would quantify it by basically saying that no matter how small of a neighborhood you choose for this limit, you would always could end up within that small region. Okay, so if you want to have a graphical, like a visual representation of this, you can look at the lecture notes or the lecture videos and look up the definition of convergence. You will see you will see a visual representation of this. But the point is that think of it as a game. Someone comes in, someone who doesn't like you, want to mess with you, comes in and gives you a really small epsilon, hoping that you wouldn't be able to get within that range around the limit, within that neighborhood of the limit for that sequence, and your task is to find the point sequence after which all terms will be that close to the limit that was previously fixed by someone who was trying to give you an impossible task. So this is the game. Someone gives you an epsilon, you find this special index after which all terms in the sequence will be closer to the limit than epsilon. Okay, so there is this limit that we are now computing. So it's the limit of, again, of a sequence that has entries that are fractions. So in the numerator, you have the sum of the square numbers from 1 squared all the way to n squared. So I'm giving you the nth term in the sequence. And in the denominator, we have n cubed. Okay? So this is an interesting limit because, well, I'll tell you why in a minute. But notice that we have the sum of the square numbers from 1 squared to n squared in the numerator, and we divide that sum by n cubed. And we are interested in this, in the limit of this sequence as n goes to infinity. It might not exist, but I'm telling you that there is a limit. Of course, it could be plus infinity or minus infinity, in which case we say that the sequence diverges to plus infinity or minus infinity. And I'm actually telling you that if you think it diverges to plus infinity, you should write inf in that box. If you think it diverges to minus infinity, you should write minus inf in the box. Okay, so there is a fair number of people who have already submitted some sort of their answer, which is good. I see already something like 70, 60 something, yes, 60, which is half of you, I guess. So please do go to itempool.com/math1055/live and try to think of this this sequence of numbers. I'm curious as to what these other well, I'm curious for, what all of these answers are. Let's finish the poll, because there is still a fair number of questions that I want to get to. So let's see. I'm telling you that it's 1/3. Okay, this is great. This is really good. So 43 people thought that it was 0. So this is what I was hoping for, actually. Let me show you why you might have thought that this is 0, this limit. What you probably did, so let me just write this again quickly. What you probably did is took each term in this sum, and you have divided them by n cubed separately. So individually, each term divided by n cubed. Okay? Which leaves you something like, well, this is the biggest of these numbers, so, and that is actually 1/n, right? So that is 1/n. So you would think that all of these numbers individually go to 0, so the sum must go to 0. Now that is where you went wrong. That is where you made a mistake. So the point is that there is a sum in the numerator, but it has n terms. Okay, so you think you are adding up really small things, but you are adding up more and more of these things as n increases. Okay, so the point is that yes, each of these terms go to 0, get smaller and smaller as n increases, but you are adding up more and more of these terms. Okay, there are n terms, so you are adding up more and more of these small numbers. So this is where you can get a false impression. You might think, okay, I'm adding up small numbers, it must go to 0 then. But we are adding up more and more of these small numbers. So in the limit, interesting things can happen. So let me just go from here to what I think that 11 of you have, at least 11 of you have done, is recognize that we have the sum of square numbers. Okay, sum of square numbers, and we have a formula for that, the sum of the first n square numbers. We had that formula from the proof by induction part. So this is simply n times n plus 1 times 2n plus 1 divided by 6. And that is what we divide by n cubed. Okay, So just quickly, let me just quickly write this as well. We are dividing by 6n cubed, and then we have 2n cubed. So I'm trying to expand this product. I won't expand the whole thing because then we have some like n squared n, and we have some constant term. But the point is that again, the dominating terms are 2n cubed divided by 6n cubed. Okay, so this is why it goes to 2 over 6, which is 1/3. Okay, so that is why this was the correct answer. Again, the moral of the story is that if we add up small numbers, but more and more of them each time, you have to think carefully about the sequence, about the limit of such a sequence. Okay, so let's move on to the next one. Okay, so this is again a true or false question, type of question. The statement is the following: if the sequence an plus bn is a convergent sequence, then both the sequence of numbers that are come from the first term an, and both the sequence of numbers that come from the second term bn are convergent sequences. So let me say this again. If an plus bn is a convergent sequence, then both an and bn are convergent sequences. Okay, so again, if you think this is true, you should be able to prove this statement. If you think it's false, you should be able to come up with a counterexample which demonstrates that the statement is false. It's not true in general. Okay. So to the previous question, we had the sum of the first and square numbers. We did have a look at that in the first chapter of the lecture notes, or the first few videos we had. I think we had definitely had problems like this. I'm not sure if the first homework had this exact same question of the sum of the first and square numbers. Okay, I like what I'm seeing. There is some sort of a divide between the answers, so there must be okay. Let me look at the chat. Okay, so there is already almost 80 submissions. Good. Again, we take the sum of two sequences, and we see that that is convergent. Does it imply that each of these, that both of these sequences are convergent as well? Let me finish the poll because we are short on time. So it is false. Okay, so many of you thought that it was true. Actually, the majority of people thought that this was true. So let me just give you a counterexample, because this statement is false. So just because an plus bn goes to some number L, it doesn't mean that an and bn are convergent. So this indication is not true. Let me give you an example. So let's take an to be just the sequence of natural numbers and bn to be the sequence of negative integers. Okay, if I add these up, what do I get? Well, I just get 0. So all terms in the sequence, that is the sum of these two numbers, is 0. So the limit is of course 0 then. So it's just a constant sequence, then goes to infinity. But think of these sequences. AN diverges to plus infinity, and Bn diverges to minus infinity. So none of them are convergent. Okay. I hope this was clear. This was just a very simple counterexample. Let's go to the next one, next problem. Okay, so always, if you see a statement like this, always try to think of counterexamples. Try to have something specific. Try to experiment with some sequences. So to see that if the statement actually makes sense, or if you can just falsify it right away. Because this is actually how research in mathematics is done. So sometimes you get an idea and you test it on many examples, and it seems like it's a true statement. So then you try to prove it. So at that point, when you think that the statement is true, that's a conjecture. Until it's proven, it stays a conjecture. And there are many famous ones in maths. So the next limit that I would like you to compute is the limit of this sequence that consists of fractions which look like the following: n squared divided by 3n plus 1. So we divide the square numbers by 3n plus 1, so one more than a multiple of 3. Okay, so again, if you think the sequence diverges to plus infinity, you should write inf in the box. If you think it diverges to minus infinity, you should write minus inf in the box. And again, try to think of, as I said previously in the first question, try to think of this fraction and identify the dominating terms in the fraction, which terms dominate the numerator or the denominator as n goes to infinity, as n gets larger and larger. Okay. So I hope this was, there's a big majority of people who voted for the same thing. Let me just quickly finish this one, because this should be a fairly easy one. Sorry if you didn't have time to vote. Basically, yes, it does something with the inf written in the box. It's basically, yes, diverges to plus infinity. There's not much to say about this. N squared grows much larger than n. So again, if I simply take this expression and rewrite it as follows, what should I do? Rewrite it as follows. Dividing by n, so that's 3 plus 1 over n. So you can see that the denominator goes to 3 and the numerator gets larger and larger, so that really goes to infinity. Okay, so diverges to plus infinity. Let's go to the next one. Again, it's a true or false type of question. So I'm asking, is it true that if an squared is a convergent sequence, then an is also convergent? Okay, so I take a sequence of numbers, I square them, and I see that these squared numbers are convergent. Does it mean that the original sequence will be also convergent. Okay, so there is already a good number of votes. I'll close the poll in a few seconds, so make sure you answer the question. Again, if you think it's true, you should be able to prove this statement if someone asks you to. And if you think it's false, you should be able to come up with a counterexample that demonstrates that the statement is false. Okay. Okay, so let me close the poll. So this was again a false statement. So again, the majority got it wrong, but that's okay. We are here to learn. So why is it false? Just think of the following sequence: -1 to the nth power. Okay, if you take the square of, well, these are just +1s and -1s, right? If n is even, then it's +1. If n is odd, then it's -1. If I square each element, each entry in this sequence, I will just get +1s all the time. So the limit of an squared is +1. Okay, it's just again a constant sequence of ones. So it is a convergent sequence. But the original sequence, an, the one that I started from, is not convergent because all it does is just jumping between -1 and +1. Okay, all it does is jumping up and down. It does not get close to any number. So there is no limit to this sequence of -1 to the power n. I hope again that this counterexample was convincing. Of course, this lecture is recorded, so as usual, you can rewatch this and hopefully convince yourselves that these counterexamples are indeed showing you that the statements were false. So the next limit I would like you to compute is an interesting one. It's the square root, well, it might not be visible. So it's the square root of n squared plus n, is the first term, and then we subtract n, okay, from that square root. As n goes to infinity, what number does this sequence get close to? 10 to. So the reason that this sequence is interesting is that you see that the term with the square root goes to infinity, and we subtract n, which also goes to infinity. So this is a infinity minus infinity type of limit, which again can result in anything. You have to consider it, look at it case by case. And for these types of limits where you have something with a square root minus something else with maybe again a square root, there is a technique to find the limit, and that is what I'll show you in a minute. Okay, so try to think of this sequence where we have the square root of n squared plus n, and then we subtract n from that expression as n goes to infinity. Okay, there's already a fair number of people who have answered the question. Let me finish this poll and show you the answer. I'm sorry if it's if we are going too fast. So it's 1/2. All right. Okay. So again, many of you thought that it was going to go to infinity. So the first term is going to sort of dominate and take the sequence to plus infinity. Many of you thought that these two terms will somehow balance balance each other, so it will go to 0 instead. So, and the actual answer is somewhere in between 0 and infinity. It's 1/2, and let me show you why it's 1/2. So this is the expression that we had to consider, and with these special types of limits, as you might have seen in one of the lecture videos where we had special types of limits, with these square roots, what we usually do is we multiply it with sort of a funny looking 1. This is just something divided by itself, but not just anything, the same expression but with a plus sign. And the reason for doing that is that then we have something of the form of a minus b times a plus b. And if you remember this famous identity that a minus b times a plus b is just a squared minus b squared, then you can write this expression upstairs as a squared, so that's the first term squared. So you get rid of the square root by this trick. So a squared minus b squared, and this is our b squared. So what you have is n squared plus n minus n squared. So you end up with n divided by by the square root. Sorry, I had to swap these. But the point is that n is the dominating term, and if you pull out an n, what you end up with is this. If you pull out an n from the numerator and the denominator, you end up with this expression, sorry. So this is just the same thing. So this is the exact same expression that we had started with. So this original expression and this one is the same thing. So if you take n to infinity, you see that this thing goes to 0, and the rest is basically just 1/2. Okay? All right. Let's go to the next question. I think this is one many of you have been asking about. Okay, again, it was half. The answer was half because it was 1 divided by 1 plus 1. Okay, 1 divided by 1 plus 1. That's a half. So the next question is again a true or false type of question. It says that if a limit is if a sequence is convergent and tends to the limit L, then the sequence of numbers that you get by taking the modulus, the absolute value of each term, and then taking the square root of that absolute value, goes to the modulus of the limit of the original sequence. Okay, so true or false? If you think it's true, you should be able to prove it. If you think it's false, you should come up with a counterexample, an example that shows that it's false. Okay. So I appreciate that we are basically out of time. But if you can stick around, just please do for a couple of more minutes while I'll show you the answer for this question, and then I'll let you go. This is something that many of you have requested that we look at. There was this problem in the sheet of practice problems, problem 4, which asked you to prove that the square root of n diverges to plus infinity as n goes to infinity. Okay, and this is this is a more general statement actually. Okay, let me. Okay, see you, Sasha. So let me go to the poll and finish the polling. So yes, it is a true statement. So again, here is the definition of convergence for the sequence AN, that it goes to the limit L. So what we have, of course, you can always rewrite this as AN being between L plus epsilon and L minus epsilon. Okay, so if you think of this and take the absolute value, well, it means that the absolute value of AN is basically less than the absolute value of L plus epsilon. If you take, if these are, let's say, positive numbers, or if these are negative numbers, then you would have the different relation, but then this one would dominate. So let me write just L plus or minus epsilon. Okay, and the point is that if I just take the square root of each side, I still get something that makes sense. And if again I try to unravel what's written here, we are going to see the definition of convergence. But now the absolute values of AN under the square root go to yes, what I should have written there is the square root of modulus of L. Yeah, that's typo. Okay, so let me finish here. I thank you all for coming to this live session. I'll see you next week, and until then, please continue to solve these problems and take care, you all.